Good morning, everyone. Welcome to OpenCV Live. I am OpenCV CEO, Dr. Satya Malik. And today I'm going to introduce you to Chehong Song, who wrote a very interesting paper at Computer Vision and Pattern Recognition Conference. This is one of the top conferences, computer vision conferences in the world. When I used to write in this conference, publish papers in this conference, it had maybe 1,500 people used to join. And I think this year, about 13,000 people joined the conference. So it has grown substantially. That shows how important computer vision has become. So Mr. Song's paper is titled Unbiased Estimator for Distorted Conics and Camera Calibration. And it's a very well-reviewed paper, got top marks there. And it talks about camera calibration. It is so important, camera calibration, when you try to do things, when you try to measure things, you need to have a very good calibrated setup. And papers like this make it possible. Camera calibration is one of those things that people have been trying to solve for ages, but every little improvement makes things ever so slightly better. And, so these techniques are very, very important. Sometimes they are very mathematical, but they are always very important. But before we start this, I also want to introduce you to Phil Nelson, who is the Director of Content and Creative at OpenCV. And if anything goes wrong on this show, he's the one who produces the show, so it is his fault. Phil?
That's right. Yes, good morning, Satya. Good morning out there, everybody. It's me, your co-host with the co-most, the second banana who is second to none. I'm also your plus one and only. It's Mr. Nelson. If you're nasty, but you, my dear friends, can call me Phil here on OpenCV Live. And I'm here to remind you of a few things that we do on every single episode of this show, the first of which is a giveaway to you in the audience. Stay tuned. Later on in the episode, I will be asking a trivia question I make up based on the awesome presentation by our esteemed guest. You will have the opportunity to win the OpenCV course of your choosing, absolutely free. You can see what courses are on offer by going to opencv.org/university. And even if you don't win today, maybe pick up a course and invest in your future in computer vision and AI. We're also taking questions from you in the audience, and we will do our very best to answer them directly, as the late great Satoru Iwata used to say. Use the Zoom Q&A button to ask your question at any time during the show, or just type your question into the chat system wherever you're watching, and we will do our absolute best to answer those during the show. If we don't get to them, we will try to follow up if you send us an email as well. We're easy to get at. Just hit up newsletter@opencv.org. But before we get started, there are a few things we should remind you of. First of all, OpenCV is a nonprofit organization that operates an open source computer vision library. And as such, we need your support. Satya, you want to tell the people why it's so important to support OpenCV and how they can do so?
Yeah, I mean, of course, as a nonprofit, we rely on support from the community. We also get support from many of our gold, silver, and bronze members, and we are thankful.
We have a couple new ones.
We have a couple new ones. Qualcomm recently became a gold member, and ARM became a gold member. Also, RunPod. RunPod is our newest gold member. They had supported us previously.
Right.
Our course takers, they gave free credits to our course takers, but now they decided, they are going to jump right in and become gold member. And we are so excited to invite Qualcomm, RunPod, and ARM has been there on the list for a while now.
Gonna have to move RunPod up higher. We're gonna have to make their logo bigger because they paid us more.
We have to make their logo
bigger.
That's how
that works. Yeah.
Right. We have to move them on the top.
Yes.
So
yes.
if your company is using OpenCV, please encourage them to become one of the members, right? We have gold membership, silver membership, and bronze membership, and almost all of the revenue we receive from donations, it goes towards the development of the library.
Right.
So,
which you can follow along on GitHub. And one of the ways you can support OpenCV is by going to github.com/sponsors/OpenCV and becoming a sponsor. We have 7 sponsors right now. We'll give them their 15 seconds of fame. Big shout out to Victor. Shout out to Jesus. Shout out to Blue Jay, Amigu, Ross Newman, Ridis Laboratories, and our newest one, DJ Greenwood. Shout out to Denzel James Greenwood, the newest OpenCV sponsor. Thanks so much. One of the other ways you can support OpenCV is by going to the OpenCV merchandise store, opencv.myspreadshop.com. Free standard shipping right now on the OpenCV shop. We've got t-shirts, buttons, stickers, bags, everything you could possibly want, bandanas for your dogs and cats, and also the very popular I Love OpenCV logo shirt design in 3 different flavors: English, Simplified Chinese, and en Espanol for our friends who speak Spanish.
That's great. And if you belong to a large company, if you're an employee of a large company, please, if you make a donation, please reach out to us, because in many companies, they have this policy that they will match your donation. So some of these large companies, Apple, Google, Qualcomm, Intel, many of them, they match your donation. And we just found out about that, surprisingly. We did not know about this program, but we found out about this program. We have registered, and now they will match your donation.
Yeah, if you're part of a big company like, your Facebooks or Apple or Google or whatever, many of them have these kinds of programs, and some of them will even match a monetary donation based on if you do some work for an open source or a nonprofit in your spare time outside of work. So if you contribute some code to OpenCV or do some work on OpenCV in your spare time, you can even tell your work about that. In some cases, they will match it with the cash amount of whatever your time is valued at for them, which is pretty friggin' cool. Yeah, and if you if your company uses a different platform, we're signed up with Benevity now. Is one of them. I know a lot of the big ones use them. Everyone from like Google to John Deere tractors use this one, but there may be other ones we're not aware of. If your company has one of those, reach out, newsletter@opencv.org, or hit me up directly, phil@opencv.org. Yeah.
Cool.
You can also become an OpenCV volunteer. Hit up the support page on OpenCV, hit up the Jot form, and if you've got time and the inclination and the skill, maybe you can help us keep OpenCV going and spread the word and spread the power of nonprofit, open source, computer vision, and AI. We believe that the most consequential technological advancements should not belong to the few, but should belong to everybody at OpenCV. Also, Phil has his own show Tuesday nights, 7 p.m. Phil's show. Check it out. YouTube.com/Phil Nelson. The same place you can find OpenCV, YouTube.com/@OpenCV official. We just passed 50.1K subscribers on YouTube. Super humbling. Thank you all so much for joining us over there. We got a lot of work to do on the Twitch channel, which currently has 89 subscribers. They're just a little bit of a difference, a little bit of a delta in those numbers, but we do what we can. Having said that, I think it is time for our presentation.
All right. The floor is all yours, please. Chiang.
Yeah, please introduce yourself and take it away.
Okay. Hello, everyone. My name is Chiang Song, and I'm a master's student at Seoul National University, advised by Professor An Kim. And may I share my screen now?
Go right ahead.
Okay.
And I'll drop the archive link for this paper in the chat as well for folks watching out there.
Yeah. Thank you. So thanks for attending my presentation, and thanks for inviting me to this great show. And today I will discuss the camera calibration, especially the CVPR paper Unbiased Estimator for distorted conics in camera calibration. And this paper is recognized for its value and receives the maximum review score. And let's start. And before getting started, I would like to introduce our contributors. Thanks to Jae-Ho Shin, Myung-Hwan Jeon, and Professor Jong Lim and Professor An Kim, we can complete this work. And this is the contents. I think most of you are already familiar with camera calibration, but some may want to start with the basic concept. Therefore, I'm going to explain what is the camera calibration first, and then go deeper into our method. And let's imagine that we are looking at the red cube looking at this red cube through a camera. The frontal face of the cube may be observed as a square in the image like this. We know that orange and green dots in the images correspond to the vertex of the cube. In fact, the orange dot corresponds to ray 1 rather than a 3 point. The green point in the image corresponds to ray 2. It means that a pixel in the image is corresponding to a ray passing through the camera. This relationship is a one-to-one mapping, so we can describe this relationship using a function, projection function, as P. To sum up, camera calibration is a process of finding parameters of the mapping between pixels and rays. These parameters comprise several variables such as focal length, principal points, and distortion coefficient. Then why is camera calibration so important? Because the mapping between pixel and ray is fundamental in camera computer vision. Many 3D vision applications necessitate camera calibration, and their performance relies on the camera calibration accuracy. Nowadays, people obtain the camera parameters by solving this nonlinear optimization. PI is the position of the point in the image, and this green term indicates the estimated position of the point using the mapping. For example, when you see a yellow 3D point through a camera, you can see the yellow point in the image. This is the measurement. And once you know a mapping function, you can estimate the expected 2D position of this 3D point. I indicate this estimated position as a green dot. If a mapping function is correct, then a position of these 2 points should be same. Therefore, we can obtain the optimal camera parameters by minimizing these photometric errors. The most widely used target is the checkerboard. This is the checkerboard. And the optimization target.
Could you describe so a lot of people may not know camera calibration, the standard notation, like K is for the camera matrix. If you could just mention what is K and D, that people would.
Oh, yeah, that's a great point. So K is a 3x3 matrix, and that matrix includes the focal length and principal points. And D is the distortion coefficient, and it indicates the distortion coefficient may be 3 or 4 or more than 5. It depends on the user choice. So I indicate the K and D as our camera parameters.
Yeah.
And back to the checkerboard method, the optimization target are the corners of the black and white squares. So we obtain the camera parameters by minimizing these two, the photometric error between these 2 points. Since the checkerboard patterns enable us to extract the target point easily, many vision packages such as OpenCV adopt this method. They first find the checkerboard corners using this function, and then they conduct the optimization process using the result of the finding the chessboard corner method. However, this method has a critical issue. An image is discretized with several pixels, and the pixel values are discontinuous. So when you zoom in on a corner, you will encounter this blurry region. As you can see, obtaining the exact corner point position with a sub-pixel level is extremely difficult.
Okay.
And this phenomenon...
Here, because we are talking about very high level, let's say you are using this for stereo, very the quality of your calibration matters a lot, right? And that is why we need it not at a pixel level, but at a sub-pixel level, right? We need where does this point exist in, like, is it 299.756, right? That is the level of accuracy we want if we want to have very high quality stereo matching, right? So
yeah, so camera calibration is a very sensitive process, so we need to get some sub-pixel accuracy.
Yep.
And this phenomenon even go further when we capture image with a low contrast sensor, such as thermal infrared camera. So this is the image captured by the thermal camera. And you see in the corner of the black square are very blurry. And returning the main equation, now we know that in case of the checkerboard, the yellow term measurement is inaccurate, which limits the overall accuracy. In our effort to resolve this problem, we found a clue in this type of pattern called circular pattern. The benefit of this pattern is its precise measurement. People use the centroid of the black block in the image as an alternative to the corners of a checkerboard. In contrast to the checkerboard, many boundary pixels decide one counterpoint, one position of the centroid. Hence, the measurement can achieve sub-pixel level accuracy. And using these patterns, we can detect these control points robustly, even with extreme conditions where the checkerboard pattern often fails. Then why have people preferred checkerboard to circular pattern up until now? Recall the equation. To achieve high accuracy, precise measurement, and the projection model are both required. Circular patterns has the former, however, we don't know the projection model. Differing from the corners of squares, centroids have no point correspondence. What I mean is that the corners of squares are projected to corners in the image. But centroid of the blobs are not coming from the original circle center. There are discrepancy between the projected point of the circle center and the centroid of the blob. To exploit these patterns, we need to track the entire 2D shape, 2D circle shape, instead of just tracking a point. The problem is that when there is a lens distortion, a circle is projected to the image like this. And there's no way to describe this distorted ellipse in an analytic form. So there's no mathematical way to describe these patterns, this shape.
So just to clarify, let's say there was no lens distortion, right? So, and some people may actually think that lens distortion, if you have a very high, the focal length is a fisheye lens kind of thing,
Yes.
it's not distortion, right? It is just the focal length effect. But in addition to that, you can also have additional distortions, right? So if only the focal length, if you had perfect, the camera center was at the center, and if the focal length could be anything, this would project to an ellipse. Is that correct? Yeah. But because you have this distortion, the lenses are not perfect. No matter how carefully you make them, especially cheap lenses would have additional distortion. It is not just the focal length, but it would have additional distortion because because of which you'll get non-elliptical shapes.
Yes. So due to the manufacturing problem, there may be a lens distortion, and it makes the ellipse distorted.
Yeah.
Next. To be specific, a circle on the target is projected to the image following these two steps. First, the circle is projected onto the normalized plane as an ellipse. So in this process, there is no distortion.
Yeah.
And then this ellipse is distorted by a nonlinear polynomial function and project onto the image. The cone shape frustrum, including the camera and circle, is called conic. So this is why I use the term of conic in our paper. So we can track the conic until the normalized plane since this mapping is linear. According to the theory of multiple view geometry, the equation of the ellipse is expressed as this. The problem is distortion. The distortion is nonlinear mapping, and it breaks down all conic properties and make it impossible to track the shape. To deal with this problem, we leverage a probabilistic concept called moments. And moments are defined as a surface integral. The first moment is defined as this, and it indicates the centroid. And the second moment represents the covariance of the distribution. The impressive point is that for any given polynomial mapping, we can find a corresponding linear mapping in the moment space. This means that if we can calculate the high-order moments of original ellipse, in normalized plane, we can obtain the moments of distorted ellipse such as centroid. So this is the key factor, key contribution of our paper. So using this theory, we complete the unbiased projection model of circular patterns. So now we find the missing piece, and the circular pattern has both precise measurement and the unbiased estimator. To combine these two factors, we complete the conic-based calibration with lens distortion. And this is the performance of our method. First, we validate our method using a synthetic dataset. We generate the ideal image taken from the random rotation and positions. And the right figure shows the average of photometric errors. Since we know the ground truth value of the camera parameters and configuration of the target board, the error should be 0. However, previous circular pattern methods have wrong projection model. They just assume the circle center is projected to the centroid. So they have wrong projection model, so their errors increase when the distortion coefficient increase. Although the checkerboard method has unbiased projection model, it shows a consistent error due to the inaccurate measurement. In contrast, our method shows the ideal errors, nearly 0.
Wow.
And this figure demonstrates the root mean square error of the estimated camera parameters by several calibration methods. Our method is superior to other methods in both accuracy and efficiency manner. And this is our GitHub page, and I want to give some code review to. So
Yeah, we can see that.
you can see the GitHub page. Okay.
Yeah, we see the GitHub.
Yeah. This is our GitHub page, and you can run the code by following this instruction. Okay, please.
This is what license is the code?
This is MIT license, and
Excellent.
we have a patent, but we don't limit this code to use any research purpose or
Yeah.
answer purpose. Just notice to me.
Okay.
Yeah, I just dropped the link for GitHub to everybody in the chat there.
Okay, thank you. And before going on, you need to check the camera model first. Our model assumes a pinhole camera model with radial distortion. So, and we also provide the method for undistorting images using our camera model. In case of OpenCV, they only support the 3 distortion parameters, but we provide a general method that can handle more than 3 coefficients.
Nice.
And next, prepare the target. We define nx and ny as the number of circles in horizontal and vertical direction. The small r is a red circle radius, and the d indicate the distance between 2 nearest circles. And all length measurements are in meters. And this is the important part. So many people ask me, what is the optimal number of circle and circle size for calibration?
Yeah, I was going to ask.
Here's the answer. Our control points are centered of this black blob. So large blobs include more pixels, so they can give us more accurate measurements. And many circles provide many optimization terms, many photometric error terms. So it makes the optimization process more robust. So, however, we cannot increase these 2 factors simultaneously since the board size is limited. So there are some trade-offs with these 2 factors. The previous circular pattern-based method has wrong projection model. So they tend to decrease the circle size to reduce the bias, and they increase the number of circles. But you don't have to do that with our method. You can increase the circle size as much as you want. And in my opinion, 4x3 circles are sufficient. So I recommend not exceeding the 7x6, the number of pixels. Instead, increase the circle size to obtain the more precise measurement.
That's interesting. And what's the procedure like? You take this board and you move it different orientations. Do you also go back slightly and then do the same thing? Do you also need to change the distance or just do the orientation?
Different distance, different orientation, also both are required. So if you proceed the calibration with some same or similar distance, you may get the calibration result that only fits that distance. So you need to vary the distance and rotation together.
Okay.
And from this step, I will demonstrate through a video later. And before going to video, I want to explain my code briefly. Yeah, and our code is divided into these 3 library, 1, 2, 3. This folder is for header file, and the util library is comprised of image handler which has an undistorting imaging function, and that's all. And detection library finds the grid structure of the centroid from the given image. So you can adjust the hyperparameter to detect the blobs in this class. And the calibration library is the crucial part. The Lie algebra class handles the 6DOF transformation. It includes all necessary functions related to the rotation and translation. I implemented this class as a static class, so anyone who needs a Lie algebra operation, just use this class. And the moment tracker class deals with everything related to the moments. The key function is this any to dp function. And this function calculates the centroid of the distorted ellipse using a given undistorted ellipse, original ellipse in the normalized plane. So I described the input and output. And the other methods are responsible for calculating the high order moments from the ellipse equation. And the calibrator class conducts a calibration. The key function is this calibrate. And in this function, you first estimate the initial camera parameters without optimization. And then it conducts the optimization process using these initial parameters. It also outputs the calibration quality. So you can decide to use the result or recalibrate after enhancing the image quality or other things. Yeah, and can you see the video?
I can see your screen, yes.
Okay.
I see, terminal windows and the GitHub window.
Yes. So I prepare some demo video for you.
Yeah.
Awesome.
Yeah, so first, just declone our repository using the declone math command. And then change the current path to the Discord car, which is the name of our repository. And in this repository, there are sample image folder. We provide some example to test our code. Yes, there's two data set, and this is the RGB data set. And this is the thermal image data set. As you can see, there are some severe distortion in the thermal image. So this is the extreme case.
So all the circles need to be visible.
Oh, pardon?
In every picture, all the circles need to be visible.
Yes, of course.
Yeah. Okay.
If there are some, in our code we check the number of circles is same as the input and exit product and y.
Right. Okay.
And let's follow the instructions. Yes, this is the dependency of our code. So you can manually install these packages, but I recommend you use just the official Docker image. We also provide a Docker file in our repository, and just copy and paste to you in your terminal. Then you can download the official Docker image. It takes some while, so I downloaded it in advance. So skip. So after downloading, you can see the Docker images named Chansung Discord car. It means the Docker image is successfully downloaded. So, and then run the Docker container using this Docker image. And this option is just for connecting the local display to the Docker container. So it may vary on your OS. And
right.
Okay. And this means I mount the current path, the Disco care folder to the /mnt path in the container. After running the container, change your path to /mnt, and you can see this path is synchronized with the local Disco care folder.
Yeah.
So, and then build the code using the CMake and make the make command. make the build directory and go to their directory and just type the CMake and make.
Yeah, Docker has really made a lot of this stuff so much simpler than it used to be. But
Yeah.
it's a little more resource, it's considerably more resource intensive, but just so
Right.
much simpler.
And after running the container, and let's start with the RGB dataset. Our code requires 6 arguments: the NX, NY, and ND, the number of the distortion coefficient, and the image directory path, and the circle radius and distortion. These 6 parameters or arguments are required.
Do you have a PDF or something that people can use to print out the circles?
There's a web page that generates them, right?
Yeah. If you go, I will provide some site.
Yeah.
Where? Here.
So
In this
calib.io, yeah.
This company provides.
Yeah, that's a very. They have all the they have very nice patterns and everything.
Yeah, right. So you can easily print this any kind of pattern. Use this site. So use the circle patterns and adjust the width and height.
That's excellent.
This is another command for connecting the local window to the Docker container. And when you run the code, the detection results are displayed on a window, so you can check them and decide whether to use this image or not. If you decide to use this image, press 1, and if you do not want to use this image, press 0 in your keyboard. And I think the detection results are good.
Yeah.
And yes, this is the result, the calibration result. We give our course parameters and 5 parameters. And the calibration quality is 98%, and the final reprojection error.
Solid.
Let's test the thermal data set. And if you don't want to verify the detection result, you just turn off the visualization option in the main.cpp file, like this. Change the checkable check detection result variable to false. And you can adjust the detection window size by revising this value.
How do you visually check the quality? So when you are using a checkerboard, right, you can look at the reprojected point and you know that, okay, this is exactly where it should be, right? How do you check here?
Now in our code, our code does not give that kind of visualization or result, but our code give you the undistorted image as a result. So you can check you can show the undistorted image and you can verify the calibration parameter is correct. And we also gave some calibration quality as a number of percent, so you can use that factor. So if you want to get some result on distorted image, you need to make some result folder. The undistorted image are automatically saved in that folder.
Right. What does the undistorted image look like?
I see later. It comes later.
Okay.
But we can see that the off visualization option is not applied. So when you revise the code, you need to build again using the make command before running.
Yeah.
And do calibration. And you can see the calibration quality is quite low, 86%. But there are 3 possible reasons. If there are severe distortion, 2 or 3 distortion coefficients may not be sufficient for that kind of distortion, severe distortion. Another reason is low image quality, and the other is the wrong camera model. In this case, we took the image carefully, so the image quality is quite good, and we already knew the camera model is pinhole. So therefore, we increased the maximum number of the distortion coefficient is solution. So we changed the maximum distortion coefficient as from 3 to 4. We increased the coefficient. Then it takes a few minutes, well, not minutes, but
So is the general recommendation that we start with about 3 distortion coefficients, right? So one of the
yes.
reasons OpenCV doesn't support is also because, you know, with more parameters, it is it can also produce bad results, right?
Right.
Because you have flexibility. So you should start with about 3 distortion parameters and then gradually go up. Is that right?
Yeah,
Okay.
right. For RGB camera, we if there are some I recommend start with 2.
2,
Two
okay.
distortion parameter is sufficient for many cases, but if the camera quality is not good enough, you can increase the coefficient to 1 and 1. So
Got it.
as you can see, the quality is enhanced to the 96%. So
Nice.
in the thermal camera, it needs 4 distortion parameters. So this is the end of video. And it concludes my presentation. Thank you for watching my presentation.
Thank you. That was
Yeah.
excellent.
Yeah,
and
so
good on time too.
That's great. One question I have is, you know, I don't remember if calib.io has the pattern. So where you have checkerboard,
Yes.
but inside that you have the circles, right?
Check.
Yeah, we used those at Occipital briefly, like a couple, like there was one circle in the middle, but then the regular checkerboard pattern. I'm not sure if
There
Calib
should
has
also
that
be
or
a
not.
pattern where you have a checkerboard. First you create a checkerboard and then you create the circles inside, right?
Yeah.
In that case, the visualization could become very easy because you can actually visualize the results of where the points appear on the checkerboard. That's easy.
Right. That's a great point. So I further implement that part in the future work.
Cool.
Thank you.
All right. Questions from the audience?
Yes.
Yeah. Do you mind unsharing your screen there? We'll do some quick Q&A.
Okay.
Sweet. Thank you. Yeah. In fact, now is a great time to do our giveaway. As I mentioned earlier in the show, one of the things we do on every episode of OpenCV Live is a giveaway to you in the audience. Everybody watching out there on Zoom right now, all currently 79 attendees for the webinar, are now entered in the trivia competition. We will be asking a question based on the presentation by our guest, and the first person to answer that question correctly in the Zoom chat will win the OpenCV course of their university, of their choosing from OpenCV University. You can go to opencv.org/university to see what courses are on offer. And even if you don't win, maybe pick up a course, invest in yourself and your future, upskill, get a new job, get a better job. So get ready to answer. The way this works is you will type it in the Zoom chat window, and the first person to type it correctly wins. If you have won in the last couple of months, please don't answer and give someone else a chance to win. So we've talked a lot about camera calibration here today, and we've looked at a lot of code. What is the variable name traditionally given to the intrinsic matrix? What is the variable name traditionally given to the intrinsic matrix? Oh, man, see, we got some real ones in here. Looks like the first one was Gustav. I think I see Gustav Nilsson. Congratulations. The answer we were looking for there was K. K is the traditional variable name for the intrinsic matrix and camera calibration. Great job there, Gustav. Please send one email to phil@opencv.org. That's PHIL @opencv.org.
This is the shortest answer that you have ever. I guess there can be a shorter one if you have a lowercase answer once.
That would be a fewer bits. Yeah.
Number of bits, fewer actions, you know.
That's right. That's right. Yeah, you're right. This has to be the lowest, like the fewest characters answer for sure that we've done so far. So yes, congratulations, Gustav. We've got a couple of good questions here. From the LinkedIn, they're asking what are the best like if you had to recommend image resolution sizes, like pixel dimensions for these calibration images, what would you recommend people do in terms of the pixel dimensions of their training data?
The opinion is there was no some absolute answer in that question. It depends on the personal experience.
Yeah.
But
Like say for example, I'll give you a for instance. Like for instance, if I had a sort of standard, even just a standard webcam here, I've got my camera here, or maybe I've got two stereo cameras or something, and I just want to use them to measure, like to look at a bird feeder, for example. But maybe it's about a meter away. What would you recommend for that situation?
in that situation, you need to capture the image in that distance, the target distance, but not only the target distance. If the target distance is so far from the camera, the optimization process may be unstable. For robust optimization, you need to capture the image in close distance. So the more the close distance means that the position of centroid may be differ. So if you take the image from close distance, you can get more robust optimization process. So the close distance images are important, and it should be included in the calibration data set. And then you capture another data set from your target distance.
Right. So a little bit of diversity is important there, because as you said, like the closer you are, the better this will perform, right? And so that was also a question people had here, which maybe Satya can also help kind of answer this as well, which is, why is that? Why is closer better for this type of calibration?
This is because when the target body is close to the camera, the position of the centroid is if you move the target in the same speed, the pixel position of the pixel value is very move fast in the same close distance. But when you put the target in the large distance and you move the target, the pixel value just almost it doesn't move in the pixel domains. So you
yeah,
need
depending on how
to-
far away you were, it
Yes.
may visually just barely move, even though you moved at the same distance. Like
right.
if you're up close and I move like this, like just a couple of inches, it moves a lot. But if I come back here, it doesn't move nearly as much, or
Yeah,
even
right,
farther
right.
away. Like, yeah, okay, that
We
makes a lot
need
of sense.
some sensitive image for calibration.
Yeah. So another way of thinking about it is that all the pixels at the boundary of the circle, they are voting for the center, right? They are saying that, okay, they are being used to estimate the center, right? The more
Right.
number of pixels they are at the boundary, the more accurate the estimate of the center becomes, right?
Yes.
In the degenerate case, you could imagine that you can go all the way back where the whole circle is just a point,
Yeah,
right?
right.
In that case, you cannot do sub-pixel accuracy,
Yeah,
right?
right. That's another good point.
Yeah, definitely interesting. For those of you wondering out there, if you had 10 on your bingo cards for the number of AI assistant bots in the chat this week, the answer was 10. The answer was 10. We're going to have to start doing like, send an email to the newsletter to guess how many there will be each week. And if you guess correctly, we like randomly give you something else. Like maybe we send out stickers or something for this. It's becoming too funny to me. 10, that's a new record, 10. By the way. So we've got a few more questions here. We got about like 5-6 minutes left in the show. Let's see. So we answered Lex's question was about distance, which we already just answered. So you just presented this, kind of just revealed this paper earlier this year, and the code and stuff, and had the debut at CVPR. Is very well reviewed. Have you gotten any contact from folks that are using this out in the field yet, that have been sent in feedback from using this method for calibration, like on real projects yet? Has anybody contacted the team?
Oh, our code got several contacts from some company and researchers. They published some issues on our GitHub page, and one company contacted us and they said they want to include our code for their camera driver.
That's great.
Yeah.
Maybe this could go. There's no reason this couldn't go in OpenCV contrib or something as well.
We plan to contribute.
I think we'd love to see it there. We
Right.
seem to have lost Satya. I think probably he's having some internet connectivity issues out there in Bangalore. But another question here from the Peanut Gallery was, does the calibration perform better, or like noticeably better or worse, depending on the input size of images? Like, say, if I'm using this on like 4 megapixel images, would the calibration appear worse or better, or would it have no real difference based on the input size?
Oh, that's a difficult and great question. When the resolution of the input image increase, the reprojection error also increased. So imagine that if we make the input image, the resolution of input image become twice, the reprojection error become twice because of the resolution. So the reprojection error doesn't indicate the calibration performance or calibration quality. So our code give another our code directly give the calibration quality using another method that verify the calibration quality.
That makes sense. That totally makes sense. We've got a few more questions here from folks out there. So this one's more of a personal one. Like, when you were working on this, or when the team was working on this, like what was the original idea? How did this start? Like, why did you all decide to go down this path?
In fact, our laboratory is a robotics lab, so we are interested in the extreme environment. So we decide to use the thermal camera, and doing calibration with the thermal camera is very difficult when you're using the fundamental calibration algorithm. So we start at that point to calibrate the thermal camera.
That makes sense. And is there any other, so aside from thermal and visual, like have there been any other, are there any other sorts of calibration that you've looked at here? Like what other types of calibration are there out there that you think this might be valuable for, aside from just the ones we discussed? Are there any others?
In field, the robotics and computer vision people, researchers use alcohol marker-based calibration, and now our calibration code just supports the pinhole camera model. But if you want to calibrate with the fisheye camera or omnidirectional camera, you can use the MATLAB or OpenCV calibration methods.
Yeah, very cool. And there was one other question out there about patents. I saw that you mentioned a patent on the GitHub repository. Can you talk a little bit about that? Like what that entails?
Dimension of our patents?
Yeah, it says at the bottom of the page here, this says this work is protected by a patent. I was just wondering what that meant.
We are prepared to. There is a patent related to this work, but we don't want to limit this work to just academic purpose. You can use this work for the business purpose and anything. We don't want to limit that, but we just protect this work to, and just we want to get some respect for another one, and we just to recognize this is our work.
Yeah, no, that totally makes sense. And with the MIT license is very permissive as well. That
right.
you can basically do whatever you want with it, so long as you include the license and tell people where you got the code from. So one of the main benefits of MIT is also it's like a paragraph. The MIT license you can fit on a cocktail napkin. It's like nothing.
One suggestion I have is if you want to make this code really popular, the Docker and everything is really good, but you can also, if you could do a pip package, then there is a much larger audience, or at least double the audience, right? Of one, because a lot of people who are entering in Vision now, they may or may not have a background in C++. And because your dependencies are very small, right? You only need Eigen and OpenCV. I think it's an ideal package for Python.
Yeah, got some folks in the chat saying the same thing. They're like, please make a Python package.
Yeah. We are planning to make the Python version of our code. We are still refactoring this package.
Yeah, totally. It makes sense. And one of the, like I said earlier, I think when you had just dropped off for a minute, Satya, that this could be a great thing to include in OpenCV contrib.
Yes,
definitely.
Prepared.
Looking forward to that. I think we just dinged the hour here. I think we can call it a show. Thank you so much to our esteemed guest. If folks want to follow you online or a social network service or on LinkedIn or GitHub, what's the best way for them to do that?
Just contact to LinkedIn or email, please.
All right, and they can find that by way of the GitHub repository, I'm sure. Satya, you want to take us home?
Yeah, thank you so much, Johan. It's the presentation was excellent, even for people. I'm pretty certain that even for people who did not know about camera calibration, your explanation and how you walked through the process, it was really very clear, right? I mean, of course, they don't know the mathematical details, but at least for this presentation, they could understand, they could follow through. So excellent presentation. Thank you so much. I also want to thank Phil for arranging this, and we need to get more of these very technical people because the audience loves it. And thanks the audience for being with us every Thursday, or almost every Thursday. So thank you.
Nearly every Thursday.
Nearly.
Yes. Yes, thanks everybody. Take care of yourselves out there. Take care of somebody else if you can, and have a great day wherever you may be. We'll see you next Thursday, 9 a.m.